So A2, so A2 equilibria. Now, what's in A2? It's most of the things would be applications of Kc and Kp. Uh, what you're going to do in A2 equilibria is we're going to start with Kw first. Remember, Kw is known as a water dissociation constant. So it's like Kc. It's an equilibrium constant, and this is known as a water dissociation constant. That's the first thing we're going to do. Now, what is Kw? Remember, water is very important on planet Earth because everything revolves around water. Okay, why is it important? Because it's your main solvent. I mean, whenever you see reactions like the human body, that's mostly made up of water. Okay, so most chemicals are just floating around in water on planet Earth. 70% of the Earth's crust is water. Plants and animals, they all survive on water. Our blood is water. Our cells contain water. So water is the main solvent. It's used not only is the main solvent, it's kind of a reactive substance as well. So it's also taking part in the reactions. So it's not just acting as a solvent, it's also taking part as a reactant. So uh, whenever you have anything that contains the two substances X and Y reacting together, the X and the Y's would be floating around in water molecules. So it will be surrounded by water molecules, and the water molecules would be and the particles would be reacting inside this solution. So that's why water is important. Now the thing with water is that water ionizes. It ionizes and it produces two ions. One of them is H+1, the other one is your OH-1 ions. So you see these water molecules and it very weakly ionizes. It's not a strong ionization, it's a pretty weak ionization. So when X and Y are trying to react, some of the water molecules that are surrounding it, they might break down and they might ionize. So let's say this one over here breaks down, and when water ionizes, it produces two ions. One of them is going to be H+1, and the other one is going to be OH-1. So your solution, it's not just going to contain water molecules, but it would also contain H+1 and OH-1 ions as well. So here's X and Y trying to react, and you have all of this happening in the solution as well. Is this clear?
Yes, sir.
Yes.
Normally your H+1 and OH-1 would be produced in exactly the same concentration because they both are going to be produced equally. So what type of solution is this? This is a neutral solution, which you refer to as pH equal to 7, right? I mean, you call it pH 7. And then you add, what's an acid? Like, what's the definition of an acid?
Any substance that dissociates into hydrogen ion.
It's a proton or H+1 donor. That's what an acid. It's a proton donor, right? So if you add a molecule over here, which is an acid, so let's say this green molecule over here is an acid. So acid is something that produces H+1 ions. So the quantity of H+1 ions in your solution would increase. So there's going to be more H+1 ions compared to, so the quantity of H+1 would be higher compared to the quantity of OH ions. So that would make, I'm just going to write it over there. So that is going to make the solution acidic. So that is what an acid does. That's the purpose of an acid. That the H+1 concentration becomes greater compared to the OH ion concentration, and that is referred to as an acidic solution. That your pH has now dropped. It has now become less than 7. Okay, is this part clear? Right? Minahil, is this clear? Bazga? Zoha, is this clear?
Yes, sir.
Acha, so an acid is something that produces H+9. So remember, all the reactions on planet Earth, probably not on another planet, but on planet Earth, they're happening in water. And X is trying to react with Y, and all of this is happening around it. So the water molecules are ionizing, but if you add an acid to the solution, there's going to be another molecule that would start producing these H+9s. And then you have a base. The base, what a base does is it does the
Sir,
opposite.
what causes water molecule to dissociate? What causes water molecule to dissociate? Do we
Yeah,
need to provide energy for it?
I'm going to talk about that. Okay, just a second. I'll just talk about it. Now, a base is a proton acceptor. So it's a molecule that accepts protons, right? So let's say I add a base to it. Let's say this black molecule, this over here, is a base. So it would start removing the H+O9s from the solution. So the quantity of H+O9s would decrease because that is what the base does. It absorbs or removes or gains H+O9s. So it removes the H+O9s from the solution. So the quantity of H+O9s would decrease and the quantity of OH ions would increase. That's called a basic or an alkaline solution. And the pH goes up. It's greater than 7, right? Is this clear so far?
Yes, sir.
Yes.
So anyways, so the whole point is, what we're going to focus on is, we're going to talk about the pH in a while. Okay? We're going to learn how to calculate pH. Everything would be revolving around pH. And we're going to understand what is this pH in the first place. I mean, what is pH 7? What is pH less than 7? What do we mean by pH being greater than 7? So we're going to talk about all of this. This is the basic concept of acids and bases and why this is important. Because the entire world's reactions depend on pH. Some reactions, like X trying to react with Y, would prefer that there is more H+O9s, and the reaction would happen more quickly. There would be some other reactions that would prefer there would be more OH ions in the solution. So, and there would be some other reactions that would require or prefer neutral conditions, like they would need both ions in the same quantity. So every reaction has its preference. So whenever we talk about solutions, there would be 3 types of solutions. There's going to be neutral, there's going to be acidic, and there's going to be basic. And every reaction has a particular preference. If the pH is affected, the reaction might stop happening. So the pH, most reactions in the world are very sensitive to pH because they're happening in water, and they will be affected if the pH changes. If the acidity or the basicity of the solution it changes, they're going to be affected. The reactions would be affected. Anyways, moving on. So, Bhaskar, now listen carefully. What happens? Why does water ionize? So we're going to talk about that now. Why does it ionize? Now, one of the reason is, like when we talk about ionization of water, we're basically talking about the bond in a water molecule breaking apart, right? And it would split into 2 ions. One of them is going to be OH ions, and the other one is going to be your H+O9s, right? So it's an endothermic process, right? You need energy for the water molecules to ionize. Bhaskar, is this clear? I mean, you have to break the bonds, right?
Yes, sir. Clear.
And the molecules are colliding, the collisions happening. So the bonds break during those collisions. Like the water molecules are not in isolation, all the water molecules are bumping into each other. So it's natural that some of the water molecules might break down to produce OH ions and H+O9. So it's an endothermic process, and there's going to be more ionization at higher temperatures. If you heat water, it's going to ionize even more. Okay, is this clear to everyone? Minail, Kausa, is this clear? Ethan, Mohammed, is this clear?
Yes.
Yes.
so water would ionize and the bonds would break because of collisions. But remember this equation over here, the one that I'm trying to copy, this one over here is an oversimplification. The drawing that I've drawn is an oversimplification. Why? Because water doesn't really ionize. I mean, all your life you've studied this. You've always studied, whenever you studied chemistry, you've always studied that water ionizes and produces H plus 1 and OH minus 1 ions. And so now the thing is, what really happens is, like if I tell you the mechanism of ionization of water, which is not important, no one is going to ask you about this. Water is a polar molecule. The lone pairs are partial negative, right? And here's another water molecule. And the H in a water molecule is partially positive, right? So what really happens is that the water molecule is going to split up. Like if two water molecules, they collide, like this water molecule will ionize and it will split up. Why? Because the lone pairs over here would attract the H positive. So in reality, what's happening is, because of the attraction from the neighboring water molecule, this H plus 1 is going to get attracted to the lone pairs over here. And the thing that's going to be produced is, there's going to be lone pairs on water and the H plus 1 will be attracted to the water molecules. Is this clear?
Yes, sir.
And you'll have your OH minus 1 that's going to just drift off. So the thing is, in reality, there is no H plus 1 in solution. Like you don't actually have an H plus 1 ion in solution, because the H plus 1 ions, they get captured by the water molecules. The lone pairs on water molecules, they get attracted to the H plus 1 and they end up forming these H3O plus 1 ions. Okay, these are your hydronium ions. So all your life you've studied that there's H plus 1 ions in solution, right? When in fact there is no H plus 1 ion in solution. It's actually the hydronium ion. This is what you call your H plus 1 ion. The true picture is that there is no H plus 1. This is your hydronium ion. Is this point clear?
Yes.
Yes, sir.
Is this clear to everyone? Remember that water would split up. That part is true. It would split up into OH minus 1 and it would split up into H plus 1 ions. But the H plus 1 ions would immediately be captured by other water molecules. The lone pairs on water molecules are going to attract the H plus 1 ions. So the H plus 1 ions are not freely roaming around. They would actually datively bond with the water molecules to form this one. So the actual equation for that is, it's this one. That one water molecule ionizes another water molecule, they split up, and they produce your H3O plus 1 ions and your OH minus 1 ions. So these two equations are considered to be equivalent. Like one of them is an oversimplification, the other one is the true picture of what's happening. Is this clear to everyone? Yes or no?
Yes.
Yes, sir.
Achha, so just don't get confused. H plus 1, I mean, they would be used interchangeably. I mean, these two equations would be used interchangeably. It doesn't really matter if you use this equation or you use this equation. They're kind of the same equation. Whenever you see H plus 1 or HCO plus 1, just remember they're basically the same thing. Conventionally speaking, they're kind of used interchangeably. Most of the time, you just use this equation, the first one. But anyways, let's talk about dissociation of water. So water ionizing. I'm going to use both equations just for clarity, so that you might meet one of the two equations for dissociation. So So let's talk about both of them together. So over here you've got water with another water molecule, and it's in equilibrium with H3O plus 1 and your OH minus 1 ion. So you've got these two reactions, which are the same reaction. Now, now look at these two reactions. They are equilibrium reactions. If they are equilibrium reactions, then there's a thing called Kc. And Kc is product concentration, which in this case is H plus 1 and OH minus 1. Divide that by your reactant concentration. So your reactants are water, the concentration of water. If I write the Kc expression over here, what do I get? I get H3O plus 1 concentration into my OH minus 1 concentration. So products divided by my reactants. And my reactants are the two water molecules. Those are my reactants. So it's going to be water concentration squared, or you can write water concentration 2 times. Like those are my two reactants. Water, so divided by my reactants, products over reactants. So I get these two expressions, right? Is this clear so far?
Yes, sir.
So now the next thing is, when we were doing Kc, I told you that if water is in large excess, its concentration is taken as 1. So in this case, water is in large excess because water doesn't really ionize much. Like there would be very few water molecules that would be ionizing. It's in large excess. Like even if 1 or 2 water molecules ionize, the concentration of water hardly changes. It doesn't change because there's so many water molecules. Like if you have 1 billion water molecules and 10 of them ionize, or 20 of them ionize, it doesn't really affect the quantity of water that much. The concentration that changes would be negligible. So remember, when water is in large excess, or anything that's in large excess, concentration is taken as a constant. So that one is taken as 1. So if you take that as 1, so you don't have to write water. It's a constant. So you just remove it from the expression. That is what you did in Kc. Like if something is a constant, you just don't write it in the expression. There's no point writing it in the expression. Is this point clear?
Yes, sir.
Now this one would be called Kw. It's going to be H plus 1 concentration multiplied by OH.
So why did you cancel out the water molecules
It's
in
in
the denominator?
it's in large excess. Now, if it's in a large excess, so its concentration would be a constant. So there's no point. I mean, there's no point writing water over here. What you could do is, I mean, instead of because it's a constant, you can combine the two constants together. Instead of canceling this, what we can also do is, we know that water is a constant, so I'm just going to pick it up from here and I'm going to take it and combine it with this constant. I'm just putting the constants together. And the same thing could be done with these two. Remember in Kc we took solids as a constant, we took solids as 1, right? So, because their value is not going to change, we just don't write them in the expression. So this is going to be Kw. Both Kw's are kind of exactly the same. Whether you use the first equation or the second equation, they are kind of identical. Once you remove water from the expression, the two Kw's are kind of exactly the same. Is that clear?
Yes.
So if you meet either one of them, it's kind of the same thing. It's H3O plus 1. Remember, in H plus 1, they're kind of interchangeably used. So that is your water constant. And the next thing is, what is the value of this water constant? Now remember water, I told you water ionizes. These water molecules, they're going to break down. Now at room temperature, under standard conditions, the amount of water that's going to be produced, or the amount of ions that are going to be produced are very few. It's 1 times 10 power minus 7 mole per decimeter cube. That's almost, remember in electrochemistry, I also told you that when we were doing electrolysis, I told you don't use H+1 and OH ions. Take water as water because you can see clearly over here that the amount of ions that water produces, that's almost negligible. That's 0 point. So this one is 0 point followed by 6 zeros, decimal followed by 6 zeros, and then there's 1. And the same applies to this. I mean, I can just copy this. So the same applies to this equation. You have the same ions. So what is your Kw? What's the value of Kw? That's 1 times 10 power minus 7 into 1 times 10 power minus 7. What do you get? It's 1 times 10 power minus 14. And what would be your unit? It's going to be mole squared. It's concentration times concentration, mole squared dm minus 6. Same goes for this one. It's 1 times 10 power minus 14. And it's going to be mole squared and dm minus 6.
So I mean Kw and Kc एक ही बात है.
You can think of Kw as Kc of water.
Right.
So this is also referred to as, what was the name that we gave to it? It was the water dissociation constant, or also referred to as the ionic product of water. It's the product of its ions. Like water dissociates, produces H+1 ions and OH ions. So it's kind of, it's basically the Kc of water ionizing. And the concentration of water is taken as 1, so you don't write water in the expression. And this is what you get. These are whether it's H3O plus 1, whether it's H plus 1, it's kind of the same thing. That's why the equation doesn't really matter that much. Is this clear?
Yes.
Yes.
So now, what would happen to the value of Kw if temperature increases? I just told you what happens if temperature increases. Would you get more ions or less ions?
More.
So you're going to get
Yeah,
more ions.
more ions.
So if you have more ions, the Kw increases. Kw increases with temperature. This value that I've quoted above, that's for standard conditions. Because you have more dissociation and more ions are produced at higher temperatures. So remember, this one is under standard conditions. I say, anyways, what do we do with this? I said, remember what we were trying to do. This product remains a constant. Kw, it always, the concentration of H+1 multiplied by the concentration of OH ion, it always remains a constant. H+1 concentration multiplied by the OH ion concentration at room temperature is always going to give you 1 times 10 power minus 14. Even if you try to change it, like if you add an acid, the concentration, so if you add an acid is added. Now when you add an acid, the concentration of H+1 goes up drastically. But the concentration of OH ions at the same time, because the acid neutralizes the OH ions, so the quantity of OH ions decreases drastically. But the product still remains a constant. Is that clear?
Yes, sir.
And similarly, if you add a base or an alkali to this, then the base neutralizes the H plus ions, and the quantity of H plus ions in the solution goes down drastically, and the quantity of OH ions in the solution, it goes up when you add a base. But the product still comes out to be 1 times 10 power minus 14. Is that clear?
Yes.
Yes.
So the thing is that not only in pure water it's a constant. Like in pure water, like this is what we did, right? Where did we do this? This thing. I told you that not only in pure water would the ionic product of water or Kw be a constant, but even if you add an acid, it would still remain a constant. It's an equilibrium reaction, so the equilibrium would automatically adjust. The H plus 1 would go up, simultaneously the OH ions would come down. There would be lesser OH ions. There would be less H plus 1 ions, there's going to be more OH ions, but the product and the constant would be maintained unless you change temperature. Remember, all equilibrium constants, they change with temperature. Okay, so there's obviously going to be more dissociation if temperature increases. Anyways, why are we studying this? So the whole point was, I told you that about the importance of this ratio. I told you that it's very important. Now we're going to move towards pH. I told you that's very important to track the concentrations of H plus 1 and OH ions, because every reaction depends on that, right? So the quantity of, like, if you're trying to plant trees, or you're in agriculture, you're always trying to check the pH of the soil, because the pH of the soil has to be ideal for plant growth. Like if the balance between the H plus 1 and OH ions, it changes, the plants would stop growing. If it becomes too acidic or too alkaline, they would stop growing. So let's say somebody is trying to actually measure H plus 1 concentration, like every day. He's trying to track what's happening to the soil. One time the concentration comes out to be 0.01 mole per dm cube, right? Then on the second day, let's say after a few rains, there's acid rain, and the soil becomes kind of acidic, and it's now 0.1 mole per dm cube. So it's like that's like really acidic. Then he added lime to the soil, and the pH dropped drastically, and the concentration of the acid decreases, right? So he's trying to track, like if there's modern agriculture happening, he's trying to track what's happening to the pH of the soil. Was mildly acidic, then became more acidic. He tried to neutralize it, became less acidic, right? So this is what's happening. Now the thing is that in science, when you try to track something, you always make graphs. Can you I mean, you know how to make graphs, right? Do you think you can plot the values on the same piece of graph paper? Like, can you, or are you using the same scale? Is that possible?
No, sir.
Okay, that's not possible because one of the values is really small. For this value, you would have to choose a different scale. This value is kind of much bigger than this value, so you can't really plot the same values. I mean, you can't intelligently use a scale if you want to plot a graph of what's happening to the H plus 1 concentration. Remember, for proper analysis, you need graphs. So the point is that if the difference in the values is too much, like there's 10 and there's 1000 and there is 1 trillion. I don't know. I think this is 1 billion, I guess. You can't plot these numbers on the same piece of graph paper because the scale is too, I mean, one of them is too big and the other one is too small. So what do people do? How do you plot these values when the difference in the size of the values is very large? Does anyone have any idea? Like you've studied math, right? What
Change the y-axis to log something.
exactly? I mean, that's where you bring in log. That is what log does. Like if the values are too small or too big, you take log. You don't take the value, you take the log of the value. What does log do? It expresses the value in the powers of 10. So this is what, 10 power minus 3, I think, or 4? Can anyone tell me? Is this 10 power minus 4? I mean, this is
Yes.
Okay, that's minus 4. What is this? This is 10 per minus 1. And this one is, I think, 10 per minus 3 minus 7, right? Similarly, this is 10 power 1, this is 10 to the power 3, and this is 10 power, I guess, 9, right? Now, when you change it to log, log expresses these values in the powers of in the power of 10. So this would be minus 4. This would come out to be minus 3. This would come out to be minus 1. Right? If you haven't studied log, just try to understand that log expresses everything in the powers of 10. So take the log of this. This is 10 per minus 1. So that log would give you minus 1. This would be 10 per minus 7, right? This would come out to be 1. In log, I mean, you can take a calculator. There's a button. Just press log. This would give you 3. And this would give you 9, right? Now, plotting these values on a piece of graph paper is kind of very easy. Minus 4, minus 1, minus 7, 1, 3, and 9. I mean, that's really easy. I mean, you can choose a scale very, very easily. Is that clear?
Yes, sir.
Yes.
Yes, sir.
Achha, so values are converted to log. Why? Because they are more manageable. Especially if one of the values is very big and the other value is, so they are more manageable. Okay, so it's a lot easier to plot these or handle minus 4. A lot easier to handle 9 rather than this big number. So that's why you take log. So remember, our whole point was that we were trying to actually track H+1 concentration. So what I'm going to do is, I'm not going to track the H+1 concentration because the value might be too small or might be too big, right? I'm going to track the log of that value. So what we're going to do is, I'm going to take the log of this expression. Okay, we're going to take the log of this expression. So it's going to be log of H+1 concentration into OH concentration, right? Taking log on both sides. And that's 1 times 10 power minus 14 and its log. And when you take log of two things that are getting multiplied, in log or in the powers of 10, they get added up. Like if you have 10 power 3, that's being multiplied by 10 power 5, what's happening to the log value? It's 3 plus 5, right? Is that clear? I mean, that's a property of log. Like if
Yes.
two things are getting multiplied, log deals in the powers, right? Log expresses them in their powers. So in their powers, they're going to get added up. This is basically 10 power 8. So when two things are multiplied, when you apply the function of log, they get added up. So it's going to be log of H+1 concentration plus the log of OH concentration, and that's equal to the log of 1 times 10 power minus 14. That would give you minus 14, right? Now you have this expression. There's one other thing that you do is that concentrations are mostly in decibels. Like just a second. So you never get a 1 billion concentration. Concentrations are always usually less than 0, right? So when you take log, you're always going to get a negative value. Like this is minus 4. In log, this would be minus 1. This would be minus 7. There would be like 1000 mole per dm cube. You've never heard about it. So concentrations are usually less than 0. So every time you take log, you get a negative value. So you're going to be plotting a graph of negative values. It's much better. You just multiply everything by minus 1. Okay, so we're going to multiply everything by minus 1 so that we don't get negative values. Is this clear?
Yes.
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 Okay. So we bring in the negative thing only because we just don't want negative values. I mean, our concentrations would be in decimals. So every time we take the log, it's going to give you a negative value. So we just multiply it by a negative value so that we always get a positive value. This thing over here is known as pH, the negative log of H plus 1. This thing over here is known as pOH. So pH is the negative log of H plus 1 concentration. Negative log of OH ion concentration is known as pOH. And together they should be equal to, this should be equal to 14. So what we're doing with pH is we're just simply tracking the concentration of H plus 1 ions. That's it. We don't track pOH because it's kind of understandable. Like if pH goes up, pOH comes down. If H plus 1 goes up, OH minus 1 comes down. If H plus 1 comes down, OH ions go up. So you don't need to track both. You can only track, or you can just simplify your life by just tracking one of them. The other one is going to be the opposite of that. So that's your pH. I mean, that's the same expression that you studied over here, which was KW. No idea what's happening. Just a second. I said this is the same thing as, so yes, same expression of KW. We've just taken the log of that. So when we took the log, it just became this expression, which is pH plus pOH is equal to 14. So both of these expressions are exactly the same. Only thing is you've taken the log of that, and I told you why you take the log. So this is how you calculate pH and pOH. Is this clear? So we're going to continue with this tomorrow then, okay? Any questions about this?
No, sir.
So let's continue tomorrow, and tomorrow we'll talk about this in more detail. Okay, then take care, everyone. Hafiz.
Thank you.
Thank you.
Chalo, okay, Thank you.